Hello and welcome to Pursuit of Perfect Systems video show coverage for the Festival of Sound, Music and Audio show. We'd like to thank our show coverage sponsors, Tellurium Q Cables, for helping us make this show coverage possible.
Good morning. Thank you very much for coming to see me. I'm flattered. And welcome to the Festival of Sound. My talk is it's kind of a combination of a history, a little bit of a history of KEF, but it's also focused a lot on the engineering. I'm one of the engineering team at KEF. I'm head of acoustics, and I've been working at KEF since 2004. And I studied acoustics at Southampton University. So, I mean, my perspective is quite technical. I've tried to put something together that covers a little, tries to give you some insight into the technical side of engineering a loudspeaker, but it's meant to be accessible. Hopefully that's about right, but we'll see as we go along. There's not too many of us, so I think it's probably easier if there's something which you're dying to know more about, or you just don't get at all, just interrupt me and we'll handle it as we go, otherwise probably forget at the end. And if you're thinking it, probably somebody else is thinking it too, so don't be afraid of doing that. Right, so what I'm going to cover, very briefly, a little bit of the background of KEF, with a little bit of an angle on it from my point of view. We're then going to kind of look at the kind of tools that you need to design a loudspeaker, or to engineer a loudspeaker, as we would call it. And then on from that, a little bit about what a loudspeaker has to try and do to convince you that you're hearing something that's a realistic version of the recording. And then specifically, why KEF approach things in their unique way, in our unique way, I should say, and particularly about Unique. And that's it. It takes about 40 minutes. Depends how many questions you have. So there'll be a bit of time afterwards if you just want to come up and ask me questions or whatever you want to do. So we'll go from there. So KEF is relatively quite an old loudspeaker company. There are older companies around, like Wavelength and Celestion and so on, but we're one of the older ones. And the reason that KEF exists is because of this man called Raymond Cook. He is an engineer by trade. He has a BSc. He was actually a World War II veteran, and when he, after the war, he studied as a mature student as an electrical engineer. He was passionate about music. Even from a young age, he played the piano. He was a classical music fan, and he managed to get a year working at BBC Engineering. Loudspeakers were always his passion, but he was actually working on tape, alignment of tape heads, design of tape equipment at the time. And during this period, he struck up a correspondence with Gilbert Briggs, who was the founder and technical lead of Wavedale, one of the UK's oldest loudspeaker companies. And whatever he was writing, Gilbert must have been impressed. And they met, and then Gilbert basically offered him a job, and not your typical entry-level job, a technical director job at Wavedale in 1955. Gilbert Briggs, though, he didn't have a really technical background, so his approach to designing loudspeakers was quite different from the way Raymond wanted to do things. Also, Gilbert was coming towards the end of his career, probably thinking about retirement. Raymond, a young man, wanted to push the boundaries, and particularly in the 60s, you had such a lot of development of new materials that Raymond was pushing to have this in the product, and Gilbert was resisting. And eventually that situation came to a head, and Raymond left. And under quite a cloud by all accounts. So Gilbert was an author. He wrote quite a few of the early audio books. There's one in particular called Audio Biographies, where he has a double-page entry for lots of people in the industry. And it was launched in 1961 when Raymond left. And they say that Raymond's entry was torn up. So they did make up eventually, but that's why KEF came about, because of Raymond's desire to do things differently, to try and use technology. So he founds KEF. Wavedale, based in Yorkshire, he lived up there, and for some reason he ended up founding KEF in Maidstone in Kent, in the southeast. So he's making life very difficult for himself, because his family was still living up by Wavedale. And this was our original premises, so not very glamorous. And it was he had some financial backing from the firm where this Nissan hut was located, called Kent Engineering Foundry, but they were actually separate companies. And there's rumours that he derived the name from Kent Engineering Foundry, KEF, partly because if he said to somebody, do you want to come and work for KEF? If you're in Maidstone, they knew what you meant, where it was. It had some local weight. Or probably more probably, if you go to the bank and you say, I want to borrow some money, you say, I'm from KEF, you might be looked upon more favourably. So he, at the beginning there were just two employees, him and, my mind's gone blank, but two guys doing everything. They set out as they meant to go on. So these are some drivers from the first loudspeaker they designed, the K1. So bearing in mind this is 1961, if you look at loudspeakers of that era, they almost all use paper cone drivers with cloth edges. Whereas straight away this is a bass driver with an expanded polystyrene diaphragm. It's completely flat, it's much bigger than a lot of other diaphragms. And a dome tweeter with a plastic membrane. So very different, very forward thinking, and actually quite risky. If your plan is to try and make a fledgling loudspeaker company, your probably best bet is to look at what's successful out there and do something similar. And they immediately said, well, no, we want to do that. We don't want to do that. We want to be innovative. We want to apply new materials. So although Raymond was doing the engineering at this stage, the company needed sales. He had to get on the road. He had to go and find a market. And he very quickly realised he needed somebody else to come in to carry over his vision of using engineering and technology. And he was very lucky, or very canny, I'm not sure which, but he found Laurie Fincham, who became the technical director in 1968. And Laurie is still in the industry at THX, but he really took Raymond's vision of how using technology, using innovative thinking, engineering, and actually said, well, how are we going to do this? Who do we employ? What other things do we need to bring in? So he started cooperation with universities, using computers, which I'm going to come back to in a minute again. Also starting to look at things in a bit more detail, actually thinking about, well, what do you actually hear when you put a loudspeaker in a room, and how does that affect what we're trying to do with design? So it's actually a lot of the kind of things that we try and still do, are things that Raymond, but also Laurie kind of founded in our company. And in this period, there's a huge amount of innovation comes out of the products. If you're at all familiar with historic KEF products from that era, you'll recognise some of them. So, coupled cavity, which is a way of getting more bass output from a box by putting the bass drivers inside. Crossover design techniques, where you could better predict what was going to happen when you put the crossover on the set of drivers. Measurements, which I'll touch on again, and Unicue, which again is quite important. And if you're not familiar with Unicue, it'll come up in a minute, so don't worry about that. So this is a really key area, and it's one that's quite critical for what we do today. I don't think a lot of people know. Before you could measure a loudspeaker digitally, a lot of engineering work that we take for granted is actually quite tricky. And KEF were one of the first, I believe they were the first companies to digitally measure a loudspeaker. So before that, you'd have to plot everything onto paper. So if you want to even do something as simple as compare two loudspeakers, you're doing it in quite an approximate way. You can plot them on the same piece of paper, but you're actually then measuring with a ruler how far apart the lines are. It's very difficult to actually then say exactly what the deviation is. It's also hard to store them. And if you want to then do another comparison, what do? Do you get two pieces of paper and line right through them, or do you plot it again? So if you sent the speaker away, you can't do that. So it becomes a bit of a bottleneck. And Laurie realised this, and computer, it was expensive, but it was becoming possible for a small company to invest in. So 1975, he worked with HP on how do you measure a loudspeaker. And once you can measure a loudspeaker, there's all sorts you can do with it. And one of the first things they did was crossover design in a more accurate way. So using the computer to help them really see what the crossover was going to do before they made it. Also some modelling. The final point's quite a key one, and I mentioned comparison of measurements. So as soon as they could compare measurements, they said, well, actually, we can use this as a tool in our production. So we make these wonderful prototypes. We don't really know what we're sending out. But once you can measure it digitally, you can compare everything. And that's really the birth of quite a famous loudspeaker range for us called the reference series. And reference is a term we hear all the time now in audio, but it wasn't always the case. And KEF, I believe, were the first people to call a product a reference series. And it's not maybe the way you think of a reference product today. That seems to be really a kind of meaning flagship, or this is the best thing we can make. But the reason the reference was chosen is to describe the production. So this is actually a quote from Raymond, but the key thing here is a name to convey the idea that every loudspeaker is subject to test and compared to a reference. So first time they could say what you're buying in the shops is to within a dB, half a dB, whatever they could do at the time. It's exactly what we intended. And that line is always then represented kind of our best technology, and we continue to make it today. And we still use the same method in production of having a lab standard and a line standard. So these would be speakers that we've developed in our engineering lab and represents what we want to make, and we compare everything to it. It's pretty much the way that every other loudspeaker manufacturer will measure their product now that computers are ubiquitous. So it gives you a little kind of insight into the history of KEF and KEF engineering in particular. I mean, we're still based in Maidstone. We're actually on the original site, thankfully not in the original building. It's a bit drier sometimes, although we're very close to the river. This is a picture, just a few of us. There's one or two faces missing there. We're kind of a serious engineering team. Everybody there has got some kind of degree in a relevant type of engineering. It's quite multidisciplinary, and that's what you find if you speak to people who design loudspeakers. There's not really a recipe for how they arrived at designing speakers, and we'll talk about that in a minute. But as a summary, the reason is that there's lots of different things in a loudspeaker. When it's working away, there's lots of different things going on, so you can get interested in it from lots of points of view. So we try and cover everything that could affect the sound. We hopefully have somebody there who really knows lots about it, and I mean a lot. And this team here, we're responsible for performance in anything that we make, anything with a KEF badge on. We're responsible for making sure it sounds good enough to represent our brand. And so for a passive loudspeaker, it's kind of stuff we've been, as a company, doing for 56 years. So we cover drivers, acoustics, cabinets, mechanical design, magnetics, all that kind of stuff. But we also make quite a few products now that have DSP in them, the LS50W with DSP to do the crossover, and some other bits and pieces. So we have people as well who specialise in working out how do you use this new technology to improve the sound as well. So, I more or less said this already, so we can go over it very quickly. But these are the kind of areas that we would cover in Maidstone. Acoustics, mechanics, prototyping, project management. Can you actually make it? Are you going to make it on time? That's quite important. This is a kind of more of a key slide for me, because this is my one of my areas really where I do a lot of work. So computer simulation is a huge amount of engineering in general now, and we try and apply that to loudspeakers. And with that, you get some other things that aren't immediately obvious. That your computer models are only really as good as the data you feed into them. So we do have to have quite a lot of work on characterising the materials we use in our loudspeakers to make sure we're getting good stuff out, not nonsense. And I already mentioned the DSP side. So computer simulation, I'm going to talk a little bit about that. Because it's an area where KEF, since we had Laurie's influence and he started us on the track of using computers, it's something where we've really tried to pioneer and figure out how do you apply a computer to design a good loudspeaker. And one of the things that we realised quite early on was that there aren't companies out there designing a bit of software that helps you design a loudspeaker. There's people who design software to model different things, so vibration or acoustics or mechanics or magnetics. And if they are designing a package, it's for somebody who's making an aeroplane or a car, because these are huge industries. And the way that we approach this was to actually say, well, let's develop some in-house software that helps us pull together simulations from different areas. So we rely a lot on our in-house software now, and in our team we've got coders who help us to keep them up to date, to develop them, and make sure they're giving us good and accurate results. So this is one of the key things that applies to kind of engineering disciplines as well. There's a lot going on in a loudspeaker. So if we just take a passive one, so that we cut down the number of things I have to talk about a little bit. But if you imagine you have some kind of electrical signal that's going in. So we've got electrical behavior going on there. There's a crossover, which is electrical circuit. There's coils of wire. Then that becomes a magnetic field. And then the magnetic field causes vibration. So we've got mechanical vibration. There's going to be some heating in there as well, so thermal there as well. We then have a vibrating diaphragm which moves the air and we get sound, so there's acoustics. So each of these domains is actually physically quite different. So in terms of simulating it, you need quite a lot of different ways of looking at the world, but in terms of specialists, you need quite a lot of people with different knowledge in different areas. I'm going to show you a few very basic examples of why you might want to do computer simulation to make better loudspeakers. So here's a very, very simple model. A tweeter dome. So we know tweeters, they look dome shaped. This is like a cake slice from it with a very sharp knife. That's just to make the simulation quicker, but it represents a full dome. We also know they move, but we can't see them move, because they move fractional amounts of a millimeter. But if we were to guess how they moved, you'd probably draw a picture like that. This is exaggerated so we can see it nice and clearly. So that's the kind of behavior we'd really like. That we have a dome in green, it's just moving backwards and forwards, and that's going to create our sound. And we need to make sure it stays roughly where it's supposed to. So we've got a flexible bit, which we call the surround at the outside edge, that allows it to move. And that's what we'd really like, and we'd really like it to do that irrespective of what signal we wanted it to reproduce. What we tend to do in simulation is put very simple signals in. So this is a single frequency, a sine wave, at 6K, which is kind of middle of the treble region. And it's behaving very nicely. But if I put in, this is now 45,000, so very, very quickly oscillating signal. Then you can see, now we get something that you couldn't guess by drawing it on a napkin. It's actually quite surprising. You don't see this with the naked eye because the movement's very, very tiny, but you can validate that this kind of behavior does happen. We have vibration, non-contact vibration measurement systems that we can validate our results with. So it looks like jelly, basically, doesn't it? I mean, we're asking it to move backwards and forwards so quickly that the middle of the dome can't keep up. That's what's happening here. And the force you need to get it to keep up becomes more than the material can provide it, and it goes into breakup. And basically, we can't use the dome at this point. It wouldn't sound good. So as a tool, very, very simple example, you can do a simulation, you can see where's it going to go like this, where's it going to go wrong, and then I can do it again. I can change something and see if I can move the area where it goes wrong higher in frequency or out of band somehow. Or I could change the materials, I could change the shape, I could change the size. So suddenly it becomes a really powerful tool for making a better tweeter. Before you could do this, you'd really be doing it with intuition, by trial and error, by trying to relate what you see in measurements to theory. Suddenly in something like 10 minutes, you can say, oh, well, if I do that, that'll happen. And then, you know, in the course of a week, you can become an expert on that tweeter. You can run 60 variations. Whereas the guy who's trying to do it in the prototype lab would still be trying to figure out why his first tweeter buzzed. So that's why we do it, because it allows us to make better products. We originally focused very much on drivers. That was the area where you see the most complicated behavior and where complicated behavior has the biggest effect on the sound you hear. But these days we're applying it to everywhere we can. In particular, we try and spot problems in measurements and then try and simulate what's going on and get a link between what we simulate and what we measure. This is a couple of animations from the LS50 project, which which is a little two-way loudspeaker with a simple box. Well, sorry, what started as a simple box. So this is, in the simple box, what we could see in the prototype was we could see the panel vibration on the back was really bad at a particular frequency. And when you see something that's really bad at one frequency, it normally means there's a resonance. On the computer, we built in all the material properties, the construction, and you could see the resonance very clearly. And I've put the cone in here so you can get an idea of how large the panel movement is compared to the cone movement. So this is up in the mid-band, everything's exaggerated, but at this frequency you wouldn't see the cone vibrate with the naked eye. But it's moving almost 50% roughly as much as the cone. So from our perspective, we've designed a beautiful driver, and now you're hearing the box almost as much as the driver.
It's a larger area than the cone as well.
Exactly. So a panel resonance can be particularly bad because the panels are big, which means they can be very efficient acoustic radiators. So you have to aim for them to move as little as possible. So that was the starting model, and my colleague Mark Dodd did a huge amount of work and came up with the construction on the right, where it's a quarter model. Again, we use symmetry to reduce the model time a lot. But you can probably, from that quarter section, see how that links to an LS50 if you've seen one. And you see the cone move, but you actually can't, with the naked eye, see the cabinet move now. So this is, again, an example of why you might want to do this. If you were trying to do it in the model shop by making cabinets, you'd be there a long time, but you also wouldn't have the insight. You wouldn't be able to say, I can see what's happening. The back panel's moving forwards when the front panel's moving backwards. So maybe I can join them together and that'll help to stop that happening. You wouldn't get that insight. The outside of the speaker also changes the sound. So sound is like waves on water, so it tends to cling to things. It's not like a torch where the light would leave the torch and wouldn't be affected by things in the kind of shadow. Sound's not like that, it wraps around things. So this is again an LS50 cabinet, and when the tweet is operating at relatively low frequency, somewhere around the crossover actually, you can see the sound's not beating straight forwards, it's actually wrapping around. And that means that anything on the surface of the loudspeaker which has a discontinuity can affect the sound you hear because it will scatter that in the same way as a kind of reflection on a pond. And we use the computer software to simulate that effect, and also then to try and shape the cabinet or design the drivers in a way where that doesn't affect what you hear. And then the final example in this particular section, just because it's something completely different. So far, I've showed you vibration and acoustics, but sometimes you come across other types of phenomena, and this is a good example. So a port. A port really, when you break it down, we use it, so for those of you who aren't as familiar with speakers, this is a port. It's just a hole into the inside of the cabinet, but it has a length, which means it has a tuning frequency. And that allows us to augment the low frequencies, give you more bass from a certain size cabinet. But it's not very big. And if we ask it to radiate a lot of sound, what you find is there's actually quite high airflow in the port. And when you have high airflow, you can potentially get turbulence. And turbulence is not desirable acoustically. It always causes noise. By definition, it always causes noise. So we do some modelling of flow. This is a CFD analysis where we're looking at a straight port and a port which has got some careful flaring on it. And you can see on the straight port, as the sound wave travels through, it creates actually enough flow to create vortices. So this wouldn't be very good. It wouldn't be very good at high levels. It would make noise and the port would stop being effective. With just some very simple shaping, we can improve it tremendously. So that's a few examples of why you might want to do computer simulation.
Have you ever simulated hi-fi tweaks? You go through a separate design of speaker and then someone at home puts a penny on the corner. That makes it sound better. Well, just for fun, have you ever simulated that sort of stuff?
Not that particular example, but there are some hi-fi things that you call hi-fi tweaks.
Yeah.
Where, from an engineering perspective, you come across them. So if I'm going to say take this loudspeaker and I'm going to measure its vibration, then it's going to vibrate differently depending on what I put it on. That's absolutely true. So if I put it on spikes, if I put it on a table, if I put it on a block of foam, So we have to think quite carefully about, firstly, how are we going to measure it and how are we going to simulate it in a way that's realistic.
Yeah.
So there are some, some tweaks like that where it's not mystery.
Yeah.
It's really engineering. It's just the interpretation is very difficult. When you come and say, well, I've put it on spikes and it sounds better, it's quite hard to then say, well, I've changed so many things. What was it that I was hearing that I like? So kind of yes and no. So I mean, we talked about a bit of KEF history, a bit of history of KEF engineering, some of the computer stuff. And I just wanted to talk about our particular direction when we're designing a loudspeaker. And this kind of leads into UniQ, why we have UniQ. UniQ is really important to us. And I think it's not always very obvious to people why we bother about it so much. So if we start by, we have got internally a very clear idea of what we're trying to do. And this kind of comes from Raymond. There's a very nice quote of his, which is quite long, but the essence of it is, we're trying to recreate the recorded music without adding anything, taking away, no exaggeration or artifice. So we still have this as our goal. You're playing your music collection, that's dear to you. We don't want to get in the way of that. We don't want to add something to that or take that away. In our eyes, a loudspeaker isn't a musical instrument. It shouldn't add some kind of character or coloration. So we try and take that and convert it into kind of engineering language. And we'll go through that in this section really. So don't want to exaggerate anything, or in fact have something missing. We don't want to add a colour to the sound. And we actually wanted to do it quite naturally. So we don't want it to reproduce sound in a way that's odd. That you suddenly go, well, something about this sounds a bit odd. And I'll explain a bit more about what that could be. And we're also quite consistent. We make lots of different types of loudspeaker, Bluetooth, loudspeakers, portable ones, headphones, and we try and make them consistent so they sound the same, and we try and hit these goals. So this maybe is very basic, but if you bear with me, if it's familiar to you. So if you're going to design a loudspeaker, you have to think a bit about what is it that you hear when you press play. And what you're picking up is sound pressures, little fluctuations of the pressure in the air around you. We can't hear all fluctuations, but we can roughly break it down in two ways. I already talked about sine waves, so frequency. So if we have a signal which is basically changing polarity with time, we can kind of characterize it by saying, well, how often is it changing polarity with time? And we call that frequency. But this roughly relates to what you would call pitch in a musical term. So I've got this off the internet. Thank you, internet. I should probably have the credit. But pitch is familiar to you if you like music. So if you take something like a bass guitar, the pitch it plays is low, plays bass, and in frequency it means low numbers. So the bass region is really kind of 20 hertz up to about 150, something like that. Mid-band, so vocals, pianos, they exist in this area, centered on around about 1 or 2K. And then high frequencies. So high frequencies, there are instruments that play notes at high frequencies like piccolos and things, but there's also quite a lot of space above that, and that's where lots of details in the timbre of instruments or little details in transients are as well. And so if you think about that whole range of everything that you might have in recorded music, it technically goes from 20 hertz to 20 kilohertz. But really the key thing here, in an engineering sense, is what we call wavelength, which is just another way of looking at frequency. But it's an incredible range, is one of the points here. So the wavelength of 20 hertz sine wave is 18 meters. Not many people have got a room that big. It's huge. Whereas at 20 kilohertz, it's 18 millimeters, which is kind of the width of your thumb. And waves physically interact with things depending on their size. So we've got this huge extreme at the bottom end where the wavelength's much bigger than a speaker, and then at the top end where the wavelength's much smaller than the speaker. And that causes quite a lot of difficulties for engineering. So the other way you can characterize sound is how loud is it? And we're kind of really familiar with this because loud sounds can be great or really annoying, and they're probably problems in our everyday lives. So But we always, you've probably heard people measure the loudness of things in decibels. And there's no reason for us to do it, really. The only reason is for convenience. Because you can scale a huge range of numbers into a very manageable range by using decibels. You've probably seen plots like this. So there's a particular scale of decibels for measuring sound that goes from 0, which is just what you can just hear in a perfectly quiet environment, up to something which actually will start to make you run screaming. And it's a nice round set of numbers, 0 to 130. So very convenient, like a Celsius scale, freezing to boiling. Pretty much the same thing. If we were to express this as a kind of pressure, so when you pump up your tyres, you're using maybe PSI or pascals. If you express the same thing as pressure, it's just a huge range. It's about 3,000 to 1. So it's just hard to deal with, and that's why decibels are used. The other thing, decibels kind of works well with your perception. So if you're listening to something and you want to turn it up, as an engineer you can say, oh, I want that 3 dB louder, and it's very easy to understand what that means. If you say, well, I want you to increase the pascals by 5, very hard to understand. So finally, we've got that window of frequency range and loudness, but we're also going to put it in a real room, which means it's really important how the sound's directed from the loudspeaker. When we hear sounds anywhere in our lives, this is our perception of what it is. Something makes a noise, the sound comes at me, and like a laser, like an arrow. And that's true, it does, but it's followed by other sounds. So reflections will fall the surface near there, and then reverberation afterwards. And these come from all directions. The reason that you're only in your conscious mind aware of that is because that's the thing that keeps you alive when you're living in a cave. When you hear a roar of a tiger, you really need to know where it is. You don't want to be confused by all the sounds. So your brain is fantastic at identifying where sound comes from. But in terms of the timbre of music and the quality of sound, everything's lumped in together. The direct sound, the early reflections, the reverberation. So we could design a fantastic speaker that only delivers great sound like a laser, and you put it in a real room and it won't sound good unless it's got a nice response off axis as well. So every other direction. And that's really important. And this is, in loudspeakers, accounts for a lot of confusion. There's this kind of, can you engineer a loudspeaker question that you sometimes see going around. And you hear kind of stories that people say, well, I had a loudspeaker and it measures like this, and they present one graph, and now we've got one like this, but it doesn't sound like that in my room. And I'm always kind of screaming at that, saying, well, that's because you're looking at that. What you hear isn't that, it's that and everything else from the loudspeaker. Does that make sense? Yes, good. So this is really, if we're engineering something, these are the kind of specs we need. And these are the kind of things we aim for to try and achieve Raymond's idea of a natural sounding loudspeaker. So cover all of this range of musical instrument pitches that you can hear. Cover the loudness that you can hear from the quietest instrument, a soft passage in an orchestra, right through to Metallica at 11. And then the final one, which I think is very key, is deliver the sound evenly into the listening room. That's kind of what I was hinting at when we say do it in a natural, reproduce the sound in a natural way. So our tools to do this are drivers. Everybody, with a few exceptions, makes sound with a speaker by moving something. It's quite simple, isn't it? You have something that looks like that. So effectively, we're making physical movement in a diaphragm that pushes on the air, and we create sound that way. We spend our lives designing these things anyway. They take us years to design something. But it is simple in essence. That's all we're doing. But there are implications for that. So the loudspeaker driver, actually, you might think of it as being the heart of the loudspeaker, but it's nothing without the enclosure. If you ever have had the chance of having a loudspeaker out on the desk while it's working, it doesn't sound very good because the cabinet's really important. If you've just got a cone flapping around, it's a bit, I guess, like having one of those fans to cool yourself down. Not a lot happens, but it flaps around a lot of air. So the air from the front just flaps around to the back. The enclosures are really important. It stops that equalization of the positive and the negative pressure. And it's only when you put it in the cabinet that it becomes efficient at generating low frequencies. But that kind of causes another problem, which is, depending on how big the enclosure is, the sound will be different. And from that, we end up finding it's very hard to make low frequencies from a small enclosure. And you've probably noticed that if you've ever listened to loudspeakers. But you can also see the same thing in acoustics over and over and over again, especially with acoustic instruments. So I've chosen string section, but you could choose any acoustic instrument. Acoustic instruments that can efficiently produce bass are big. And this comes down to that wavelength thing. You have to have something that's big compared to a wavelength. Like a pipe organ, for example. The other thing is that we can't use just one driver. Really, we can't. I mean, there are some people who try it, and I kind of admire them for trying, but you can't if you're trying to reproduce everything. And that's because we have to move quite a lot of air to get low frequencies efficiently, and that means we have to have quite a lot of area. So lots of drivers or a big driver. And then that causes us a problem. We saw that tweeter animation earlier on, these horrible resonances that you get in diaphragms. And the bigger the diaphragm, the bigger the cone or the dome, the lower that happens. So we need small drivers at high frequencies, and we need big drivers at low frequencies. Again, this is that wavelength thing, big wavelengths at low frequencies, small at high. So how do we handle that engineering-wise? We use different drivers that do different things really well. So this is typical three-way system. The signal comes in, we split the bass off and send it to a driver that's really good at reproducing bass. We split the mid-range to the vocal region, that's kind of a piano kind of center of the keyboard, and we send it to mid-range, and then the high frequencies to the tweeter. And you have to have some kind of filter circuit to separate them out, which is called the crossfilter. And that's all there is to it. The problem is, once you split the signal up like that, it's really hard to put it back together in a convincing way. Really difficult. And one of the main issues is that these are in different places on a typical loudspeaker. So what does that do? So here's an example. Just a two-way this time, but we've got a tweeter doing high frequencies, a woofer doing low frequencies. I'll turn the box sideways just because it fits on the screen better. So the high frequency sound comes from the red dot, and the mid and the low from the blue dot. And I'm putting a pulse into this. So in the crossover, that gets split up into the bit of the pulse that's got high frequencies, and that goes to the tweeter. The bit of the pulse that's got low frequencies, that goes to the woofer. And if I were listening somewhere over here, I'd be equal distance from these two drivers. And I'd get quite a nice pulse, in theory, around about here. But the problem is, if I'm somewhere else, the distance between me and the tweeter is going to be different from the distance from me and the woofer. And you can see they don't add up correctly. It's like dropping two stones in a pool of water. You get two sources of sound, you don't get one. So what's the right signal? Where should I design the speaker to have the best response if it's going to do this? And our opinion is, well, you can't. It's kind of broken. You can't do it. And come back to the point I mentioned earlier on. You might think this is okay because sound coming towards me is all right, but as we know, you're in a real room, you're going to be hearing those reflections. So it's really important that the speaker sounds good in other directions too. So that is why KEF have Unikey. So if you're not familiar with it, this is Unikey. It looks like a normal cone driver, but instead of a dust cap, there's a tweeter in the middle. This was invented in 1988 by Laurie. And all he's trying to do here is put two drivers in physically the same space so that you don't get this problem. So I took my simulation and I put my two drivers in the same point in space. There you go. Now, what we can see is we get this pulse of sound which is spreading very evenly. So I should be getting pretty much the same signal if I'm anywhere along here. And if I'm moving around, I'm always the same distance, you know, between me and the tweeter, and between me and the woofer. That's why it works, and that's why we're really keen on it. There's something else a little bit more subtle. So it's not just the position as well. You need the character of the driver's sound as you move off axis to be the same. And UniQ can do that as well. So, you know, we're kind of familiar. You walk around the back of the speaker, the treble will start to drop off. So we need the way that drops off to be the same from the woofer and the tweeter. So there's a little bit more to it. So 1988, I realised when I was putting these slides together it was 30 years ago, and we probably should have done some kind of celebration of UniQ. Happy birthday, UniQ. We've been continuing to work on this. This is a UniQ, it's actually from a product we don't make anymore, but it's a very different picture to the one I showed you earlier, a few slides ago, the C35, the first UniQ. We've been investing a lot of engineering effort into this in the last 30 years to try and make it really, really good. I mean, our view is that the idea has always been really, really good. And then we've been working on the execution to make the promise actually come across really well. We, in the last 10, 12 years, we've made a lot of traction using computer analysis to make the UniQ work really well. We measure our UniQs by generation. I've got a list on the last page, but latest is generation 12. So that's quite a lineage when you listen to a KEF system today of development. So what makes a UniQ today different? There's really 5 key things, so I'm going to go through them. So the first one is, if you take a tweeter that works really well on front of a loudspeaker and you put it in the middle of the cone, it might not work very well anymore. It's quite a different acoustical situation. And we did some work in around about 2004 to say, well, is there any way you can get it to work really, really well? We had our doubts at the time, but it was quite interesting because out of that we found that you can, but the key is actually quite simple. You have to have just the right shape of dome, and you have to have just the right shape of cone, because the cone's going to affect the sound of the tweeter as well. If you do that, you can get a wonderful response. So these are stripped back models with domes that don't have resonances and perfect surfaces with no discontinuities. But what you can see is, if you take the dome and you put it onto an infinite wall, in a pulse you do actually see something going on at the outside edge here that kind of ripples around. But if you get the shape of the UniQ cone just right, you can actually get something that's better. So that was 2004. We applied for a patent on that configuration. Every UniQ since has followed that. And that was kind of a breakthrough moment for us. The first time we applied that was on the Muon project. It caused us another headache, though. We saw this kind of jelly-like tweeter. If you want to make a really good tweeter, you don't have a lot of freedom over the shape of it. It's one of the few things that you can control. And what we found was that this shape that worked really well for the acoustics actually worked really badly for the mechanics. So we had to come up with a solution for that. And again, this is something we patented again in about 2004. But our tweeters are actually more complex than they look. From the outside, you just see the dome surface. But behind, there's actually 2 parts. So there's the dome. If you zoom into the corner, you see the front part there, and then the back part cuts off the corner. And the key thing is it creates this triangle. You see triangles in engineering everywhere because they're really rigid shapes. If you bolt a triangle together, it can't go anywhere. And that helps enormously to keep the tweeter rigid. It means our aluminium tweeters rigid up to about 40 kilohertz. Whereas if you take most 1-inch tweeters in aluminium, it got to about 30, something like that. We do make quite a lot of drivers where the cone is designed to move quite a lot. So for example, this is a two-way speaker, so this cone is having to move a fair bit at low frequencies. And normally on a kind of mid-woofer, you'd have quite a big seal around the outside edge. We call that the surround. Typically kind of looks like a half-roll kind of shape. And what we were noticing was that you could get the tweeter itself to work really well, but if that sound hits that rubber ring, it will scatter. This is the kind of thing you get. And it was having a huge effect on the sound directly to the listener. You can see this kind of repeat of the pulse of the listener. And that's why on a lot of our drivers now you'll see a very different looking surround. This is a Zen Flex surround here. The idea is it's kind of low profile. I guess like, you know, stealth aircraft. That makes it sound really good, doesn't it? But the idea is that we don't have any interruption in this surface. This surface remains totally smooth. So it's actually not for the benefit of the cone driver, it's for the benefit of the tweeter. The sound from the tweeter can pass over that without scattering. And again, that's something we have a patent on as well. This is a very distinctive aspect of our Unikeys. It's the cover over the tweeter. I haven't got any animations for this, but this was an interesting one because we were asked to come up with a way of protecting our tweeter because people damage tweeters very easily. Anybody who's worked in a shop is going, oh yeah, I know. But we were really, really anti this in engineering. We didn't want to put anything that would compromise the sound. And me and one of my colleagues, Mark, we actually did a fair amount of work for our sister company, Celestion, who make drivers with phase plugs in. And so we had this idea, why can't we make some kind of phase plug that protects the tweeter, but also we can control the way the sound comes from the dome. And that's where this came from, the tangerine waveguide. So the explanation of this is a bit detailed. I'm very happy to talk to you about it. I think it will go over most people's heads, so grab me afterwards. But what happens is when you put this on, you can get actually a better response than without it. And again, this is something that's quite dear to me because I ended up getting a PhD from the work on it, so that's very cool. I've talked a lot about the tweeter because that's really one of the main challenges in a Unikey because the tweeter is very different. In a way, the mid-range isn't, but we still want to guarantee really good performance. One of our key aims at the beginning was a lack of coloration. And with drivers, people talk about the sounds of cone materials. And that's kind of a strange thing in a way, you know, because what you're hearing isn't the material, is it? It's the sound. So, you know, how is that being transferred to you? Really, we ended up saying, well, it's got to be via bending. If there's no bending in the cone, if something's just moving rigidly, how can the material possibly influence the sound? So the bending, you know, really is lumped in with breakup. So if there's no breakup, we don't get any bending, and then you don't have a character because of aluminium or because of paper or whatever you're using. So we made a conscious effort, you know, really since Blade, to say we want all of our drivers to just move rigidly. We don't want them to break up. But finding a way to do that we could apply to every product we make has been quite challenging. In the end, the way we handle it is we use aluminium cones in a lot of products, like this Q350. Aluminium is great, it's very light, very stiff, but it's got no damping. So if you make a driver from it and you don't do anything special, it will have a character. It will have this very metallic character when the thing breaks up. And I'm sorry for showing graphs, but it's just to illustrate the point. The red line here is a mid-range driver made of aluminium with no attention paid to controlling the breakup. And this is the character here, this big peak. It's incredibly loud. So even if you're using this driver in a different band, you'd hear that. It will come through somehow. The crossovers don't cut things off immediately. So we wanted a way of using aluminium for all its good attributes without this problem. So simple engineering solution really. We combined it with a material that has the attributes it was missing. So at the neck of the cone, so between the voice coil that drives the cone and the aluminium, we have a rubber piece. So the rubber's got lots of damping, but it's not particularly stiff. But by fine-tuning the shape of that, we can get it to absorb that peak. So you end up with something like the blue line. So that's something you'll find on pretty much all of our Unicubes. The only exception being Blade, which has rigid operation by a very complex system, very detailed structure of a cone with a rib structure behind it. And just a final thing, we're still trying to improve Unicube. This is actually something from one of our most recent products, the new R series, which is only really just coming onto the market now. So we noticed on some of our measurements a little glitch that we weren't totally sure where it came from. And this is a good story because it kind of typifies the way we approach things. So having noticed it, we then set someone the job of trying to find out where it was coming from. And they figured out that there was this sound travelling down the gap around the tweeter and then bouncing back out. So when the tweeter was operating, you got a kind of sound after the main sound that was a little bit delayed and a little bit coloured. He verified that by measurement and then mimicked it by simulation. And then once we've got to that point, we can use a simulation to improve it. And we reworked the arrangement in the Unicube so that we could have, at the back of this channel, instead of having a hard end to it, we could have a soft absorbent path that carries on into the motor system to go with that. So that's a brand new feature on our series. And again, it's something we applied for a patent on. Yeah, so I mean, we're quite proud of this kind of investment in engineering in the Unicube in particular. So 30 years of trying to perfect this one idea. It's taken us a long way. I think if you had the opportunity to listen to the first Unicube and the most recent one, you'd be amazed at the difference. It's a real transformation. And you know that the benefit for us is that the Unicube patents run out. We've got all these other bits of technology now that mean that we can build a concentric driver like that better than anybody else in the world. And why are we bothered? Well, it's really directivity. It's directing sound into your listening room in a really natural way. And again, a graph, but so I'm sorry about that. But you won't see a lot of manufacturers showing you loudspeaker frequency responses, which is for whatever reason. But you know, this is one of the R3. You can see the red is the typical frequency response you see, so pretty tidy. But one of the key things here is what does it do in other directions, which is quite hard to say because there's a lot of other directions. This is one where we typify it. So these three other curves, the blue, the green, and the purple, firstly, an average over what you might say is somewhere someone might be sitting, like the width of a sofa. And then the green, an average over the whole front half with what the sound is doing. And then the purple, an average over all directions. And the key thing here is that they're all smooth. You don't suddenly say, oh, when I go off axis now, I've got no mid-range or I've got a big resonance. That's the key for us, and that's what makes KEF loudspeakers different from other loudspeakers. So I've talked a lot about engineering. Listening is something that's really important as well. So we use listening to inform our engineering. So when you come up with something new, we tend to try and prototype it, and then we try to take it in the listening and gauge how much of a performance change there is, or hopefully an advantage. And you do occasionally tidy up something on a measurement, and then you take it to the listening room and you say, that's quite hard to hear. I'm not sure, I'm not convinced. But I must say, I've never ever had a situation where we've got a better measurement and it sounded worse. So I mean, that really means that we can use our tools very well to make progress in our loudspeaker engineering. Correlation is very important. The engineering tools will predict engineering measurements and things like that, but you need to keep your eye in to gauge what kind of a difference that's likely to make. And the only way you do that is by listening throughout the whole process. That's it, that's all I'm going to say. So I hope I've given you a little bit of an insight into how we approach things. I think it's really, really in line with what Raymond was originally thinking about when he founded KEF. And in our department, we're quite proud of that. So we'll keep trying to push things forwards. And yeah, that's our goal. Innovative, thoroughly engineered, exceptionally performing products. So thank you very much. Thank you. Are there any questions? Anybody? Yes.
Why did KEF stop using the couple cavity base version?
That's a good question. It kind of happened before over the KEF. I mean, the couple cavity, the main benefit is efficiency. You can get more bass output for a given enclosure size, but you trade bandwidth too. So it restricts where you can cross over between the bass and the mid. One of the things we do on most of our speakers now is try and use quite a high bass to mid crossover, because we think the crossover is less audible because of that. So if we went back to couple cavity, that would be one of the main problems. So our crossover bass to mid is typically between 300 and 400, depending on the product. With couple cavity, it used to be down at about 120, 130. So that would be my case. If you mean at 350 to 400, or it's more about when you have a passive crossover in particular, the lower you move that, the bigger the components you need, the more distortion you get from them, and then also the more interaction there is between the driver, the cabinet, and the crossover. So that's one of the reasons we're pushing it high. The other is that the crossover actually introduces some time smearing. And you can minimise that by moving the crossover points up as far as you can still get everything else to work. So that's one of the reasons I never think subsat systems sound quite right, because it's very hard to get like an 80 hertz crossover to sound really good because of this time smearing effect. Anyone else?
Is there any considerations for different driver materials, like for these tweeter in particular, instead of aluminium? Is what I mean.
Yeah, I mean that's a good question. I think sometimes our perception of our tweeters is maybe damaged because we're not using something exotic. But the reason, aluminium is actually a fantastic material. I mean, titanium is, I think, viewed as being a lot better, but in fact it's better to use aluminium. If you make the same tweeter in aluminium and titanium, your aluminium one will break up the same. It'll be a little bit more damped. You could have more exotic materials still, but and maybe that's a direction for the future. But the key thing for us is, it sounds very crude, but a dome tweeter in a foil is basically a milk bottle top. It doesn't have a lot of strength if it's flat. You can push your thumb through it and open your milk. The detail of what makes it work really well is 90% of it is in the shape, and that's an area where we've really tried to excel. And you'll see other manufacturers do the same thing by using innovative shapes for the tweeter, a combination of different parts. There's a few other people using different materials as well. You can get performance that is beyond, a standard aluminium tweeter.
So it's more the engineering as opposed to the material, really, is what you're saying?
Yeah, I think that's what I'm saying. But there are absolutely some materials out there that are fantastic. Like beryllium, for example. But the cost of it is very prohibitive. I mean, there's no way we could make a beryllium tweeter in a Q350, but we can give you the best aluminium dome tweeter you can buy, for example. So we're quite focused on engineering where we can apply that across a broad range of products.
Sure. Would a Unicube tweeter always have to be a moving coil speaker? You couldn't stick a ribbon or anything like that?
No, you could. You could. It would be hard to engineer it to work really well, I think. I mean, the key purpose of Unicube is that the two drivers appear to be one. So the directivity of the mid and the tweeter has to match. And a ribbon's directivity is quite different from a normal circular cone driver. So you'd probably have more trouble with that than anything else. So a ribbon tends to have narrow vertical directivity and wide horizontal. To build a mid-range that did the same would be challenging. I'm sure you could get something working, but I don't think it's an avenue we'd pursue.
Ohmage, you didn't touch on that at all. I appreciate ohmage changes. You're speaking like say it's 6 ohms or 8 ohms,
yes.
but in the real world it's fluctuating.
Yeah, that's right.
How much difference does it make if it say jumps up to 20 or 30 or 50 ohms? How much difference does it change? Because obviously it's resistance in the speaker. How does that change the sound?
Well,
is it something you have to consider?
Yes, we do. I mean, the rating system impedance. We use nominal impedance, which is kind of a loose term. It's something like it's more or less averagely this.
Correct,
Yeah. It's abused a fair bit as well. But it's really determined by, even if you take a driver, it doesn't have a pure resistance at all frequencies. If you measure it with a multimeter at low frequencies, it'll have a pure resistance. But it's a coil of wire, so it rises at high frequencies because of inductance. And then around where there's a lot of movement of the coil, which is at the low frequencies, you'll see a peak as well. So it is inherent in moving coil loudspeakers. And the kind of catch-all workaround is, in theory, it doesn't matter if you have an amplifier which has got zero output impedance, which is like infinite damping coefficient. So it's more of an implication for the people making amplifiers. We do try and be a little bit generous. We don't want to make something which is an incredibly difficult load and nobody can appreciate the sound unless they buy incredibly expensive amplifier. But yeah, that it's.
Is that in, because it was never touched on at all in the presentation, but is it something that, is it an important factor for you when you consider designing a new speaker?
It is a factor. I don't know if I'd say it's the most important. And in a way, the thing that's a little bit ironic is your ability to make the loudspeaker an easy load to drive is more difficult on a lower price product. There are techniques of making a loudspeaker easy to drive that actually Laurie and his team pioneered, but they always involve putting more crossover components in and costing more money. And for a product where we're really trying to give the customer really good value for money, it's better for us to spend that budget somewhere else in the speaker. So we do consider it, but I think if you spoke to any amplifier designer, they'd say we were the scourge of their line. Now, loudspeaker designers, they don't understand. So yeah, there's a bit of that. I mean, the other thing is we design a few active systems now, and that's quite interesting because it gives us the ability to break the rules a little bit there.
With multiple amplification, which is obviously the answer to do that, isn't it?
Yeah, and also the ability to select an amplifier that does one job really well. Because if you're an amplifier manufacturer, there's a lot of unknowns. They don't know what speakers you're going to connect to. So they have to be a bit cautious about how they design the circuit and make some assumptions about what we're doing as loudspeaker manufacturers. If we're putting everything into one enclosure, we can, we've got the advantage there. We know this amp's only going to be used on a tweeter, its bandwidth's only going to be this, the tweeter's electrical load looks like that, and that's one of the reasons you can get really good performance from an active speaker is that.
Is active going to be spread across the range at all? Is something you might be looking to see?
That kind of depends on you guys. I mean, LS50W, it was a fantastic project. It's something from an engineering point of view we've been dying to do. Because the passive crossover, in a way, is quite primitive. But we manufacture things that we hope our customers buy and enjoy. So we're kind of keen to see. We'd love it to be a runaway success, and then if it is, you'll see more and more stuff like that. And I think it's probably not only us keeping an eye on that in the industry.
Connected with that, now that you have the LS50W in your lineup, have you considered doing a gaming to fit as a studio monitor?
Well, it's been discussed because we have found that there are music producers, people who work in studios cottoning on to Unicube now. That happened actually before the Active. We were quite surprised by how many people were finding out about LS50s and using them in a studio situation. So the thing is, it's not our focus. Though. I mean, our focus is very resolutely still remaining home audio. So I couldn't say either way. But it's quite nice to see. Sometimes you hear this perspective that a studio for home has a different requirement from a studio from a loudspeaker for a studio. A loudspeaker for a home has a different requirement from a loudspeaker from a studio. But I don't really buy that. I think the advantages of Unicube are particularly important in a studio because you're quite often listening in the near field and moving around a lot around the desk. You want the consistent sound coverage over that wide area. So it's nice to see that some people are cottoning onto it without us even really targeting that.
didn't know where to come in. I think.
Yeah, I think I'm holding up the next group, but I'll be around so we can have a chat.
Thanks very much, Jack. Thank you.
Thank you.